Today we're going to go through basically a couple of the practice problems on our final exam. And so we'll go ahead and get started. So the first question, and it will be on your exam as well, for your final exam as well, we'll cover kind of topics of corrosion. So let's go ahead and get started. So let's read the problem. I'm reading a technical memo from a student. They give me a following table of electrochemical cell potentials for several different materials at standard conditions, and it is incomplete as seen below. So if we are at standard temperature and pressure or standard conditions, what does that mean? Well, we know that our temperature is room temperature, 198 K. We know our pressure is 1 atm. And we know that we are looking at our electrochemical cell with our kind of positive terminal here, negative terminal here. It's in this kind of 1 molar solution, right? So 1 molar solution of its own ion, so whatever that material is, so 1 molar solution. So that's the situation that we're at right now. We have several different materials. So we have platinum, we have cadmium, we have iron, magnesium, cobalt, tin, and nickel, and copper. So the first part of this question asks us, fill in the table and correct any incorrect calculations. What are standard conditions? List them all quantitatively. So we've already kind of done that. So we've killed out this one. So now let's go ahead and fill out this table. So we know that we are going to want to go back and look up the values in this page of our lecture notes or our lecture slides. This bad boy right here. So let's go ahead. I'm going to turn off, or I'm going to flip up my computer, and we are going to work in our favorite Mathematica to solve this problem. So, if I remember correctly, and we'll kind of take a peek at that in a second. So we had copper. So we know that the basically copper reaction is going to be 0.340 positive. I think we had tin as well. So tin is minus 0.136 volts. We had platinum too, I believe so. That is going to be 1.2. We had magnesium as well. That was minus 0.26, or excuse me, 2.363. I believe we had iron. Thinking back to it, well, minus 0.40. We had CD. I think we had cobalt too. Minus 0.43. Cobalt is equal to minus 0.277. And I think we had nickel as well. There's a lot of problems, or a lot of questions. Minus 2.50. And I think that was it. So let's go ahead and let's take a peek back at our problem and make sure that we have all those values. So I'm going to scroll back to here. Let's see if we've captured all of those expressions. So we have copper, platinum, tin. I'm pretty sure we have all of those now. So those are our standard potentials. So we know, I'm going to flip back now, and we know we have our terminals set up like this, the positive and negative. So if I have my electrochemical cell, I have my positive here, which we designate initially as your kind of cathode material. This is our anode. My E naught of the cell, which is in here. So E naught of the cell is going to be equal to E naught of our cathode, which is the positive terminal, minus E naught of the anode, which is our negative terminal. And then we'll be able to see which material is actually really going to corrode. So flipping back, once again, sorry for all the flipping. Let's go ahead and calculate these values. So for the first cell, it's going to be PT minus Cu. So we kind of knew there's a mistake there already. So let's just kind of calculate the rest of these. Sn minus Ni, Co minus Sn, Fe minus Cd, and Mg minus Pt. So those are our values. These are all the kind of the correct values for this equation. But let's kind of see let's kind of qualitatively see if this makes sense. We know, for example, for the first problem, platinum is more electronegative than copper. So it wants to grab electrons more. And we know, let me flip once again. We know if we set up like this as your standard kind of potential. Let me draw here. If electrons are flowing from here to here, so if my electrons are traveling from my negative to my positive electrode, we know that that voltage that we measure is positive. If it's flowing in the opposite direction, the voltage that we are going to measure is going to be negative. So that is, again, which is the real anode material, which is the real cathode. So let me flip once more. So that makes sense for platinum. Sn and nickel, same way. And look, the clear example also is magnesium, right? We know magnesium wants to give up electrons. Platinum really wants to take them. That is a large negative voltage there. So we filled out the table, and we've basically corrected any incorrect calculations. We've listed them all quantitatively, so we're going to go there. So now it's asking us, place an X next to materials that will grab electrons. So the materials that will grab electrons are our more electronegative materials. So those are the ones that aren't going to corrode. So for this first one, let me change color. So materials that will not corrode, it's going to be here. Let me look back at my, so in materials not going to corrode, because it's positive, we know that this is grabbing electrons. Let's look again. Oops, opposite here. So that material is going to grab electrons. And what else? And the next two are the same way. So all of these are going to grab. So there we go. Then it says, place a Y next to materials that will not corrode. Well, that's kind of a kind of a ridiculous question, but anyways, so materials that are not going to corrode are the ones that grab electrons. So it's the same one. So the materials that will corrode, so corrode in those cells. They're losing electrons, they're undergoing oxidation. Which reactions will be spontaneous? Prove this quantitatively. Well, I know that my delta G is just going to be equal to, or my delta G naught is minus N, oops, excuse me, minus N, Faraday's constant, E naught. So I know that when delta G naught is less than 0, that is going to be spontaneous. When delta G naught, when my Gibbs free energy increases, that is not going to be spontaneous. Not spontaneous. So I know here, if this, I know this is positive, Faraday's constant, I know this is always going to be positive. This is just my number of electrons. This is the cell voltage that I read. Now I know if E naught is positive, I'm going to have a spontaneous reaction. So this is spontaneous, this is spontaneous. These will not be spontaneous because my delta G naught will be greater than 0. So, all right, we're moving along through this problem. So let's look at the last kind of part of this question. The students tested a combination of iron and cadmium in non-standard conditions. So they measured the voltage to be 0.1 volt at 1000 K. Where are the electrons flowing here? What material will corrode? And what material will electrodeposit? What is the ratio of the concentration of products over reactants? So when we're not at our standard conditions, we know from our lecture notes, we need to go to and utilize the Nernst equation, which is all that, all that kind of good stuff right here. So let's kind of rewrite it. So let's rewrite it over here. So I know to use my Nernst equation, E minus E naught is equal to, let's go back to here, so minus RT. Oops. NF natural log. Let's just make sure here. So see, minus RT over NF natural log concentration of products over concentration reactants. So we know temperature, we know R, we know N, we know F. We know E naught from our problem here. We also know this is 0.1 volts. So R is 8.314 joules per mole K. This T is going to be 1000. F is going to be our Faraday's constant, which is, I believe, 96485. Let me double check that really quickly here. Yep, 96485. Coulombs per mole. and n is just going to be, again, our basically number of electrons. So when we have this combination of Fe and Cd, we previously found that E naught was what? FeCd, our E naught was equal to minus 0.037 volts. So initially the electrons are flowing from where? Well, Cd was actually grabbing electrons from iron, but once we measure our E naught to be positive, so if we have our cell here, so we have our Fe, which is positive, our Cd, hook it up here. So we know now the electrons, if we read a positive voltage, this is our negative electrode, this is our positive electron, we know now the electrons are flowing from here to here. So now we know that this electron corrodes, this material corrodes. We know this is going to be electron positive. So again, so we've answered this question, we've answered what's going to corrode, what's going to electrodeposit. Now we just need to solve for what's the ratio of the concentration of products over reactants. Well, that's a trivial solution at this point, right? Because we have essentially our equation right there. So I'm going to increase this. So I'm going to set this as a variable. So E naught FeCd is this. So I'm going to solve 0.1 minus E naught FeCd, set equal minus 8.314 times 1000 K. All of that divided by 2 times 96485, and let's put another parentheses just around it. Probably horrible if you're good at coding, seeing this happening here. Times log of x, and we're solving for x. And that's it. So that's your ratio of products over reactants. So that's the solution to the first problem. So that's all they wrote on this one. So next time we're going to get to my favorite example, which is polymers, and we'll talk about that a little bit later in the next video. So thanks. Have a good one. Bye.